So today we're going to be talking about data structures. So data structures, .cpt. And what is a data structure? Well, it's a method of organizing your data. So method of organizing data. So depending on how we organize our data, we might get different benefits out of it. And we're going to talk about what sort of trade-offs certain structures have a little bit later on. But for right now, we're going to start off, like we always do, with a simple hello world. So int main, std cout, hello world, std and l, hashtag include iostream, make a little CMake list. We're going to be using GCC on Linux for today's talk instead of the usual Windows environment, just because it's a little bit more convenient for me. But everything I'm talking about should work just fine on the Windows environment. So we're going to start off like usual. CMake, minimum required version, 3.21. Project, we're going to call this data structures. It's going to be a C++ project. We're going to add an executable, yes, and that's going to be from data structures.cpp. So let's make sure that this runs, and then we'll ask, what is the simplest data structure? Well, we've already met him, std vector. So what is a std vector? It is a linear collection of contiguous memory, elements stored in memory. And what does this word contiguous mean? Well, it means that every element is going to be packed in close to each other, right next to each other. The plus in your C++ is rotated 45 degrees. What? Yeah, but what does this mean? Yeah, but I don't understand. Oh, that's a good point. When we talk about C++ projects in CMake, we write them as CXX. Why they decided that they were going to use that convention, I don't know, but they did. So let's go and build a very simple vector. So we need a couple of things here. First off, we need a struct vector, and we're going to template this struct on type name t on some type. And now we need a few bits of data here. We need a size t. Size t is an unsigned integer, the same size as a pointer. We use them a lot for measuring the size of memory. Since it's the same size as a pointer, that means it can index as much data as a pointer can. So a size t has about the same size as the memory we can access. So they're very useful for accessing memory. And we need some obvious thing, right? The size of our data. And we need a pointer to our data. But we're going to use good modern techniques, right? And instead of writing a raw pointer, hashtag include memory, we're going to have a std unique pointer to our memory. Okay? So what else do we need? Well, oftentimes vector has another piece of data, size underscore capacity. And why would you want this extra capacity? What's the difference between size and capacity? Well, size is the amount of data actually used, whereas capacity is the amount of data created. Why would we want to think about both of them separately? Well, if we're going to be growing our vector repeatedly, right? Instead of giving them exactly what they need, wouldn't it be a little bit better to give them a bigger block that they can grow into, right? Because every time we grow to new memory, we have to make new memory, which requires allocating new space on the heap, which requires scanning the heap to find space big enough for us. And then we have to move all of the data we've already put in the vector into the new location. So there's a copy of everything we already have to the new thing. So if we're doing a copy every time we add one element, that's going to be really slow. But if instead we do a copy every time we double the size, things works a little bit better. So we have this separation between capacity, how much we currently have allocated, and size, how much we're actually using at this moment in time. Does that make sense? So let's start off by creating an empty vector. And in that case, we're going to go memory equals new t array, and we're going to give it some default size. So 16 we'll say. Then we'll set the size to that value, 16, and we'll set capacity to 0. Nothing has been used so far. And we're going to add a couple of other constructors. So we're going to add one that takes a vector by reference. This is called a copy constructor, and we're just going to use the default one. So when we decide to copy things, we're just going to use whatever std_unique pointer does. We're going to make one which takes an R value reference, which is something we've not talked about much about, but this is what's called copy, a move constructor. And again, we're going to do the default thing. And then we're going to do other versions of those. So reference operator equals. So we're going to create copy and move assignment operators. So these define what happened when we're creating a new variable from something else. And then these are defining what happens when we overwrite an existing variable with something else. And now we'd like to be able to resize our vector. So we need a new size, so size_t and new size. And what happens when we resize? Well, we're going to create some new memory. The std_unique pointer new memory is going to be equal to new t 16. And we're now going to want to copy, not 16, new size. And we're going to want to copy over all the data from the old memory to the new memory. So we're just going to do that very simply for right now. Did copy, which we can take first and last. So it's going to be the old memory dot begin, and then the old memory dot begin. And we're going to need a new variable here. So size_t, smallest size, is going to be equal to std_min of new size and size. And we'd like to copy over memory dot begin plus smallest size into the new memory dot begin. New memory. We'll use get to access raw data. So what is happening here? Well, we're figuring out the smallest size. So either the new size if we're shrinking or the old size if we're growing. And then we're going to copy that size. So if we're shrinking, we're only going to copy the amount we still have room for. And if we're growing, we're only going to copy the amount that was already there. We're going to copy it into the new memory. Then we can overwrite our memory with the new memory. Sound good? And then we want to do a little bit of bookkeeping. We want to set our size equal to new size. And we want to set our capacity equal to size. We want to set our size equal to smallest size. And in fact, we can save the variable. So we'll just set size equal to smallest size. And then we're going to set capacity equal to new size. So we're now able to store this amount of memory, and we actually have used this amount. So either all of it if we shrunk, or however much we already were using, if that makes sense. There is another common operation called reserve, which is similar to resize. It's going to use a lot of the same mechanics, so we're just going to call resize, but it's a little bit different in the capacity. With resize, we actually set, what I'm actually describing here is size equals new size, is what resize does, whereas reserve does the minimum of the two sizes thing. So we're going to set up here, set size equal to the min of new size and size. And we're going to save that size_t, saved size. And then we'll set size equal to saved size. So when we resize, right, we're telling it that we want to use all of the memory. All of it's been like committed. So this size that we're requesting, we're using all of it at the moment. So the capacity should be filled. When we reserve, we're saying, actually, I'm not going to use all of it at the moment. Just give me some amount. I want to reserve this much, but then I'll actually fill it in later, if that makes sense. So if we know that we're going to do a bunch of like pushbacks, we can reserve space for all of them so we don't have to reallocate it all in the meantime, but don't actually claim that we've used the memory, if that makes sense. So now let's talk about push. So we're going to do void pushback, and this is going to take a const t reference back. And the idea here is we're going to take this value and we're going to add it to the back of the array. So first check we want to do is check if size is equal to capacity. So what does this mean? This means that the vector is currently full. In that case, we want to resize. And now there's a lot of dispute over what kind of resizing algorithm to use here. But the simplest one is just to double the size. So we're going to say 2 times the current size. So we'll make it twice as big, but we don't actually want all of that used. So we're going to reserve 2 times the current size. Then we're going to say that we're going to increase the size by 1. So plus size, or size plus equals 1, whichever floats your boat. And we're going to access the memory, and we're going to access the size point of it, and we're going to set it equal to back. So we're just going to update what we're currently storing at the back. Another common operation is void pop back, and this kind of does the opposite. So while push back adds something to the back, pop back removes the back. And the implementation for this is actually incredibly simple. We can just shrink size. So size is now 1 element smaller. It's kind of a cheating thing. And before we do this, we should make sure if size does not equal 0, then we shrink it. So we're just saying, hey, that last thing, don't actually assume it's there anymore. That's the simplest possible way we can implement this. So it now becomes part of the unused capacity. And the other most common operation is like random access. So actually accessing something, and we can just tie this off to memory right now. So operator square brackets, size t, the element, and we're just going to return memory square bracket size. We'll just kind of toss this off to the stud unique pointer for us. And let's make sure that this compiles before we go any farther. Nice. So this system where we have a block of memory, and then we manage a size and capacity for it, allows us to resize data that's all right next to each other. When data is right next to each other, it's very good for what's called cache locality. So in a modern CPU, when we load new data, we don't actually just load that data. We load that data and several kilobytes of its closest friends and neighbors. So if we expect to, we're under the expectation that if we're going to load A, we'd also like to be using B, C, and D too, if that makes sense. But if we want to use A and then we want to use E, right? They wind up being in different places, and we have to go fetch more memory. There's some details here about cache misses. We're going to talk about this a little bit more in the next lecture I do, which will be on design patterns, I believe, and how trying to fit nicely into this cache locality thing really speeds up performance for us. But right now, we're going to talk very, very briefly about some of the things you can build on top of a vector. So things that can be built on top of a vector. I always spread my sequential data all across RAM so that no one place gets too hot. Nabu, how could you? Nabu's trying to be slow. His games will be slow, they'll run terribly. He's an Unreal Engine though. So things that can be built on top of a vector. We can have a stack. So a stack is like a stack of plates at like a cafeteria. So the first thing put on is the first thing taken off. So you put a new plate on top, right? Then when the next person comes along, they're going to take that same plate. Or you put a pile of 10 plates, right? Those 10 plates are going to be taken before the rest of the plates. Can I have a stack of pancakes instead of plates? Sure, whatever floats your boat. The way to think about the stack is what we have here, right? Where we're manipulating the same end. So we're going to push back and we're going to pop back. That's stack type behavior. That's in contrast to a queue where we have different end behavior. So to support a queue, we would need something like push back and then pop front. Or we would need something like push front and pop back. So with a queue, we're working on opposite ends, if that makes sense. So we add things at the end, and they don't get processed until everybody who showed up before them gets processed. Different end behavior. And then there's another cool one called a ring buffer. In a ring buffer, we have like a fixed size, and then instead of doing this behavior where we resize when we get too big, we just start overriding the first thing. So when data stops being relevant after it's been used, right, we can just push something in the back and then move the back to the front once we run out of space. And then keep moving through until we get to the back again, and then go back to the front and start overriding. So this overriding the front when we run out of space behavior it's very useful when you don't want to spend time to make a new allocation. So they show up a lot in like low-level embedded system stuff and networking drivers, which is hopefully something I'll talk about at some point. So I've sketched the world's simplest vector implementation here, but don't actually use it. It would be better to use the versions in the standard library. So don't use this vector. There's a lot of like edge cases we haven't fixed here. Use stood vector. People spend a lot of time optimizing and fixing the data structures found in the standard library. So they're there for you to use. Like stood vector in the standard library tends to have something called a small vector optimization. If you only have a few elements in the stood vector, it doesn't even need to make an allocation, which is something our system here doesn't even support. So we're going to save this vector, and then we're going to make it we'll copy the file name from CMake, datastructures.cpp. So we're going to talk about another data structure. This one maps one element to another. You always write your own data structures from scratch to avoid another JavaScript left pad incident. It's okay, Nabu. Everyone has the right to do more work than they need to. And don't go around teaching my students to do unnecessary things. This is the kind of stuff that gets you bogged down and never getting a game out the door, you know? Hence why I'm gonna do it, so that I can never get a game out the door. Haha. So, to talk about the ability to map one thing to another, we're gonna have to build up a couple of intermediate or building block things. So, to talk about mapping values, we need to talk about lists, and we need to talk about hashing. So let's start with a list. So when we're talking about a list, we wind up building a chain of what are called nodes. So we have struct, and we're going to template, type name, t, list, and then inside of the list, we're going to have a struct called a node. So what does this node do? Well, it's going to store a t, so value, and then it's going to store a node pointer, next, and often it's going to store a node pointer, previous. If we don't have the previous node, this is called a singly linked list. If we have both, it's called a doubly linked list. Actually, just tell an LLM to write it for me. This is like the correct use for large language models. Writing the repetitive code that's like not worth our time to write. So only this is a singly linked list, whereas having previous as well makes a doubly linked list. So now our list is going to have a stud, unique pointer, team, node, and we're going to make one of these, a stud, unique pointer, node. So this is called the head of the list, and this is called the chain pointer. So we follow these pointers down, and their job is to keep the next piece of the next node in the chain alive. So when this gets thrown away, everything farther down the chain goes away. But there's a problem. If we were to set this node as a stud unique pointer, well, then we get a cycle. The next, so the first node will be pointing to the second node, but the second node would also be pointing to the first node. And so they do some stuff to keep each other alive. So I end up with this cyclic dependency problem. So with lists and graphs, which we'll talk about in the future, we have to be aware of this cyclic dependency. So we want to make sure that nodes aren't pointing to more than one thing. Hence why this previous thing, the doubly linked list, is going to be a weak pointer, not a smart pointer. So what does the head do? Well, it keeps a reference to the first node. And we usually also have a node pointer last if we're a doubly linked list. So when we create our list, it's very simple. Head is just a null pointer, and this is already looking a little bit simpler than the vector was. So now, if we want to add something similar, void push. So we void push our const t reference back. And what do? Well, there's two cases. So if head is equal to null pointer, and we're going to make sure that everything we haven't set yet is equal to null pointer. So if head is equal to null pointer, then head is going to equal a new node. Otherwise, we're going to take, and then we're going to set the value, so head value equal to that. Otherwise, we are going to try and find the last node, which is why keeping track of it is easier. And up here, we also need to keep track the last node is equal to head.get. So we can access the last node, and the last node's next node is going to be equal to a new node. And we're going to set the value of this to back. Well, actually, we're going to save this pointer. So auto reference new node is added to the chain. And now we need to set the previous node. So new node previous equal to the last node. And we need to update the last node to the new node. And then the final creme de la creme is that we need to make sure that the new node's value is equal to the value we're setting. So we wind up having this system where we have to go find the end of the list and update it. So add a pointer back to the previous and then add the information in, if that makes sense. So popping is kind of easy, right? We can see from this. To pop, we remove the last pointer, updating next and last. Well, it turns out that lists are faster to push and pop at the beginning than vectors are, but they're kind of worse at just about everything else. So faster to manipulate the front, since manipulations on the front with a vector require copying everything else in the vector, whereas manipulations on the front of the list do not. But what do we mean by it? Pretty much everything else is slower. So let's go and look at T-reference operator square brackets. So the random access. So how do we do this? Well, we have a node pointer, the head, the current, which is going to be equal to head. And then we're going to go while index minus index is greater than 0. So if we want to access the zeroest thing, we're already there. So current is pointing to where we want it to be. Otherwise, we need to go current equals current next, and then we need to subtract 1 from the index. So if index is 1, we need to go 1 deeper into the next. So pretty much every operation involves scanning through the list. Sometimes we can do it from the front, sometimes we can do it from the back, but either way, we have to jump through all the places in the list. I remember how we were talking about how things being contiguous is nice for modern CPUs. Well, since the list allocates these new nodes at different times, there's no guarantee about where in memory they'll be stored. So if we do a bunch of list pushes right after each other, so A, B, C, D, they're very likely to be contiguous. But if we have 2 lists, so we're pushing A, 1, 2, B, 3, C, 4, 5, D, right? A and D are much further apart. Whereas if we were using 2 vectors and we were pushing, we'd wind up with A, B, C, D, 1, 2, 3, 4, 5. So lists create what's called fragmentation, whereas vectors are contiguous. So I mentioned there was another thing we needed to talk about first, which is hashing. So hashing is the idea of taking some value and reducing it to a number. So there's a bunch of techniques for how we can go about doing that. One popular one is the FNV1A hash technique, where we take a bunch of bytes of data, right? We multiply it by some prime number, and then we XOR it, which is kind of like an OR with itself. But the general idea here, right, is we just take our thing, split it into a bunch of bytes, and then do some manipulation to combine all those bytes together. So take our struct and apply some formula to combine all its bytes together. Sometimes that gets a little bit more interesting. Like for a string or a vector, right? You probably don't want to be combining together like the size and capacity information. You want to be combining together all the memory pointed to for the vector. So sometimes figuring out how to get all of the bytes is a little bit difficult, but fortunately there is a function or functoid thing technically, but a function-like object called std_hash that the standard library provides for us. And it has overloads, if we go check std_hash, for like every single thing in the standard library. So you want to hash your error code or your unique pointer or your optional, it all works. Unfortunately, the standard does not define what hashing algorithm they should use. And I know for a fact that different implementations use different algorithms. So the results of stud hash are not consistent between compilers, which is unfortunate. But for our purposes, all we need to know is that hashing takes a value and reduces it to a number. Well, how is that useful? Well, we're going to make a new thing, struct dictionary, and this is going to have two things. So template type name key and type name value. So what we're going to do here is we're going to have a vector. So we're going to use a stud vector. Since we don't really want to use these implementations ourselves, I'm just writing them out very simply as an explanation type thing. You want to go use the versions that are optimized, which for maps, for dictionaries, is stud map or stud unordered map, depending on some things we'll talk about later. So we're going to make a stud vector of stud lists and of stud pair, key, and value. And let's make sure that we are including vector and list. And this will be what's called a hash table. So the idea here is we have two operations. Void insert, which takes a const key reference key and a const value reference value, and value reference lookup, which takes a const key reference. So when we insert things, we add both a key and a value to the dictionary, and then we can look up a value based on only its key. So we can add like strings, right? Representing words, and then the value can be definitions. Hence the name dictionary. We use a word to look up the definition. So what does this actually look like? So first order of business, we're going to stud hash our key, and this is going to get us a bucket. So the idea is we have our hash table, and we're going to make it a certain size. So when the dictionary is created, we are going to resize the hash table to some existing size, like 10. And now we're going to take our hash, and we're going to reduce the bucket down to 10. So hash table.size. So this percent symbol is called modulus, and it's not a common mathematical operation that people are used to seeing. Modulus gives you the remainder of a division. So what does that mean? Look at some examples. So we have 2 divided by 5. Well, what does this give us? This should give us 2, but what's 5 times 2? That's 4. So there's 1 left over. So 2 divided by 5 gives us 2, whereas 2 modulo 5 gives us the 1 left over, if that makes sense. So we get this pattern that repeats over and over again, where we take infinity, so the range of all possible numbers, and we map it down to 0 to 4. So what happens if instead of saying 5 here, we use n? Well, instead of 0 to 4, it becomes 0 to n minus 1. It turns out that this range, 0 to n minus 1, happens to be the bounds of an array of size n. So modulus is very good at wrapping a value around so it always stays in the bounds of an array. So what are we doing here? We're taking the hash of the key. We don't really care how it gets hashed. All we care about is that it gives us some number back. And if we look up stud hash and we look at its operator, you see that it should give us back a size t. Now remember, we mentioned that size t is an unsigned integer, so we can't have positive integers in there, that is about the same size as memory. So we have this unsigned integer, and we're now reducing its range from every possible size of an unsigned integer down to just the size of the hash table. So this bucket is now going to be a number. Bucket is now a number between 0 and size of the hash table. So now we're going to access that bucket in the hash table. So hash table, bucket, and what is that bucket? Well, it's a list. So we're going to push back a stud pair of key and value, representing the key and the value. So now the back of this list has the key and the value. So now let's go look at lookup. So we're going to do something very similar up here. we're going to take the key and we're going to hash it into one of the buckets. Then what we're going to do is we're going to take the bucket list, which usually has a very different meaning, which is going to be the hash table at that bucket, and we're going to look at for auto-reference key value in the bucket list. If key value got first, so the key is equal to our key, then we return the value, which is key value dot second. So what winds up happening here is we can very quickly look up things. Ideally, as these lists start getting long, we resize the dictionary, the hash table, to have more elements in it. The fullness of the bucket lists is called pressure, and more advanced dictionary implementations do their best to try and minimize the amount of pressure. Like always, don't actually use this dictionary implementation. Like, it's very bad. Like, only having 10 keys and never doing anything to resize to reduce the pressure is going to make that this starts performing very bad very quickly. But what can we use instead? Well, the standard library gives us stood map and stood unordered map. What I presented here is an unordered map. So stood map uses a tree, and this is a nice segue into talking about trees to look up, whereas stood unordered map uses a hash table to look up. There is another version, stood set and stood unordered set, which use almost the exact same method, but instead of having a value, there is no value. So with a set, you don't want to map to something, you just want to see if some key is present or not, which turns out to be something that's very useful. Being able to very quickly see if something is or is not in a set. So there is another wrinkle with the hash table. There's two types of hash tables. So the first is called close addressing, which is what we did, where you look up in another list. So you have a hash table filled with lists. With open addressing, you put everything in the flat hash table and have some other method of determining what is or is not a collision. So the reason for this is what happens when two keys hash the same value. So say Bob is a 2 and Sally is a 2. Well, they need to go in some list together, and in closed addressing, we just put them in an actual list. Whereas with open addressing, we instead have a flat hash table and we add more information to the cells to build a list in implicitly. There's trade-offs between the two, and the distinction is kind of hard to understand. So just remember that a hash table needs some list of things so that it can resolve what happens when two keys wind up hashing to the same thing. So the last thing we're going to implement, so let's go and put dictionary here, and then we're going to grab datastructures.cpp. The last thing we're going to implement is called a graph. So a graph winds up looking a lot like a list. So we're going to have a struct graph, and then we're going to have a struct node, just like in a list. And we're of course going to template type name t, so we can store some data on the graph. We're going to have a t value, but now our nodes are a little bit more complicated. We're going to have a vector or a list or some other data structure of node pointers for the parents, and we're going to have to thus include vector or a list or whatever. And we're going to have another vector node pointer for the children. So in a list, nodes have one parent and one child. In a graph, nodes have any number of children and any number of parents. The last thing worth mentioning is there is one more thing in the hierarchy here between lists and graphs. In a tree, nodes have one parent and any number of children. We may put an extra name like a binary tree or 2 children or a quad tree or 4 children, but in general, one parent, any number of children. So it's very similar. We have a lot more traversal type techniques that we build with these. And the idea of walking from a parent to a child is very similar to the idea that we did with a list. So graphs are just like super lists. And what do we use them for? Well, one common example is maps. So we can treat a map as a graph where like all of the cells that an enemy can be in are in the graph. How is this useful? Well, we can mark cells as being occupied or unoccupied, and then we can search through the graph to figure out how we can get to some point. In fact, this idea of searching through a graph that has obstructions in it is called pathfinding. And there is another method of storing a graph, which is called the matrix method. So the idea with the matrix method is we have a matrix whose dimensions are the number of cells. So we have a 10-cell graph. So 10-cell graph gives us a 10 by 10 matrix. Each cell represents if there is a connection from the row cell to the column cell. So what does that mean? If cell 10, 0 is 1, is true, that means that you can get from cell 10 to cell 0. But if cell 0, 10 is false, you can't go back. There might be some other path you can take to go back, but there is no direct connection between these two nodes. So the list-like representation is good when there are few connections. So in like the map example, right, a cell is likely to only connect to its 4 or 8 neighbors. If you have 100 cells and each cell only connects to 4 neighbors, it doesn't connect to 96 other neighbors, right? So the matrix representation would have a lot of zeros and would be wasting a lot of space. But when the cells have a lot of connections, so say you have 5 nodes and all 5 of them connect to every other node, the matrix representation starts being better because you don't have the added overhead of managing lists on every node. So these 3 data structures, it turns out, can solve just about any problem that exists in computer science. But there are some better data structures that solve very specific problems. Like red-black trees are usually what get used to represent maps in the unordered method. So remember, we mentioned that there is a stood map, which is implemented by a red-black tree, which is a very specific type of tree with some extra constraints put on the nodes. Whereas a stood unordered map is implemented with a hash table. So there are a bunch of data structures like red-black trees, which are good at solving very particular problems. But these 3 data structures, so 3 and 2 halves, I could say, that the bases are vector, dictionary, graph, and then the offsprings are like trees and lists, are very good at solving just about any problem. Although there might be more specific data structures that can solve specific problems better. But if you learn how to use all of these and get pretty good at them, they'll carry you very far. Also, as I've been harping on, these implementations, like for the graph, it's not even really a full implementation, that I've been making shouldn't really be used. Use the versions in the standard library or in some other library. People put a lot of effort into optimizing those libraries so that they're very efficient, whereas these are designed to be simple and easy to understand. And one of these more specific data structures is something called a delegate. So what is a delegate? A delegate is a stood vector of functions. So we'll make a template, type name t, a return, type name multiple, t args. It will be a function that returns t return and takes t args. And of course, we need to include functional in order to use this. So how is this idea of taking a vector of functions useful? Well, another word for a delegate is an event. So we can add functions to the event that get called when the event happens. So what's an example of this? That would be something like main loop start or main loop end. Those could be decent events that get called every frame, like at the start of the frame and at the end of the frame. Then we can run some extra code when the frame starts and when the frame ends. In fact, there's a whole style of programming called event-based programming, where pretty much everything you do is based on these delegate type events. And that's going to segue into how we're going to end today, or more accurately, how we're going to start the next lecture, which will be on design patterns. So one of the design patterns is the event pattern, or the subject-observer pattern. And we're going to talk about how we can use a delegate, which is based on a vector, right, to implement this pattern, as well as several other patterns.